Hello everyone. Continuing on applications of differentiation. In today's session, we will be looking at the increasing and decreasing functions and the first derivative test. First, we're going to look at the increasing and decreasing functions. Now, remember from the last lecture, we talked about the definition of an extrema of a function, basically where the function is going to be having a maxima and minima. And then we learned how derivatives can be helpful in finding where the function has a maxima and minima. So in this lecture, we're going to look at where the functions are increasing and decreasing, and then apply the first derivative test to find the relative extrema of a function. So let's start with the definition of increasing and decreasing functions. Now look at the graph on the left-hand side. Notice this graph first decreases, it's going down, and then it stays constant, which is given by a horizontal line, and then it starts to go up. So notice as the graph is decreasing and then constant and increasing. Now we're going to first define what do you mean by increasing and what do you mean by decreasing. So we say a function is increasing in the mathematical context. A function is increasing on an interval when I pick up any two numbers. Suppose I pick up numbers, say x1, and I pick up a number x2. So when you pick up two numbers such that x1 is strictly less than x2, as you can already see that, and then you look at the function values at those points. Even the function values are exactly like they're this kind of less than equal to in the similar fashion as x1 and x2 are. So what we're saying is that f of x1 is also less than f of x2. So if you're saying two values in an interval where one value is less than the other, their function values also obey the same format. That means f of x1 is strictly less than f of x2. Now let's look at when a function is decreasing. Now if a function is decreasing, if I pick up two values, say I have values x1 and x2, and clearly x1 is less than x2, but when I look at the function values of those points, the function value at x1 is definitely more than the function value at x2. So that means the graph is decreasing. Now what happens at constant? Now notice at constant what happens. No matter, if you pick up two values, say x1 and x2, the function value is going to be the same for a constant function. Okay? Now, we're going to talk about the derivatives, the test also, but here I'm going to show you certain things. Okay, so let me just talk about this function here. I'm going to just do a little erasing so that I can actually show you what I'm going to talk about. Okay, so let's look at this function value, say x1 and x2. Now, remember from the chapters in differentials, we said that the differential of a function gives the slope of the tangent line at that point on the function. So fx1 is basically, so if I take the differential, so this is a point f of x1, but if I draw a tangent line at x1, suppose this is my tangent line, okay? So I'm drawing a tangent line at the point x1 and f of x1. Let me just remove all the extras I have here. Okay, so this is the point I'm drawing up. So at this tangent line at the point x1 and f of x1, we note this tangent line, if you remember, that this tangent line is given by f prime of x evaluated at the point x1 and f of x1. Okay, so that, notice what is this tangent line? This is a straight line and the line is going down. So that means the slope, which is basically given by f prime of x at this point, evaluated at this point x1, f of x1 is negative. So whenever you notice, you pick up any point over here, draw a tangent line. All the tangent lines will have negative slopes. And that's the way we look at a decreasing function. We see a function is decreasing, so every point on that function where the graph is decreasing is going to have a negative. The value of the derivative at that point, all the points on the decreasing part of the graph is going to be negative. Now, we already know when it came to constant functions, what was happening at constant functions. So pick up any point because the constant function is a horizontal line. And we know that the differential of a horizontal line is 0. So that means any point over here, the differential is going to be 0. Now let's look at the part of the graph where the function is increasing. Okay, so where the function is increasing, if I draw a tangent line. So tangent line, remember, gives us the slope of the function. The slope of the tangent line is given by the derivative of the function. So if I draw some small tangent lines over here, so that means the slope of this tangent line is always going to be positive because the tangent lines are all going, these are straight lines and they're all going up. So what is the relationship? If you have an increasing graph of the in an interval, the derivative at each of those points on the increasing part of the graph is always going to be strictly positive. So this is a very, very important concept. I can see this. Let me write it much more nicer here. So this is the, oh my gosh, wow. Okay. Okay. Sorry. So this is, remember, the tangent line to the graph at the f prime of x is negative at the point x1 and f of x1. Suppose if this is the point. Okay. So let's look at the test. How do we figure out the test? Now we've already done the concept over here. Just we're going to put it more in a formal manner. If a function is continuous on a closed interval, okay, let a function fx be continuous on a closed interval and differentiable on the open interval, then if the derivative is positive for every x in the open interval, we say function is increasing in the closed interval. If the derivative is negative for every x in the open interval a to b, the function is decreasing on that closed interval. And if f prime of x is equal to 0 for every x in this open interval, we say the function is constant. So this is a very important test which will help us to find whether a function is increasing or decreasing and also give us the intervals. Okay, let's look at some of the guidelines for finding intervals for increasing and decreasing functions. Now, if your f is continuous on an interval a to b, it's an open interval, we would like to find open intervals on which the function is increasing or decreasing. So the steps are, first of all, we find the critical numbers of the function. And then we use these numbers to determine the test interval. After that, we look at the sign of the derivative of the function at one test value in each of these intervals. Then we use the previous theorem, just the one which talked about whether the function is increasing or decreasing. Now these guidelines are also valid if the interval is say negative infinity to b, a to infinity, or negative infinity to infinity. It just asks the intervals to be open. That's the most important part. So this is the theory. And now guys, we are going to go and do examples. So let's start with our first example. Now, The first example says, find all the open intervals on which the function x cubed minus 3/2 x squared is increasing or decreasing. Now clearly this nice little function is a cubic function which is continuous and differentiable. So the only thing we need to do is find the critical numbers. For that, we take the derivative of the function, which is 3x squared minus 3x, and then put that to 0. And when we solve it, clearly 3x is common, x minus 1 equals 0. So the critical numbers are at 0 and 1. Now remember, these two critical numbers determine the three test intervals. Remember, the critical numbers will tell us what are the test intervals. And also notice, as these are critical numbers, and if we remember our the critical numbers, and from the graph I would say we can see that we have a horizontal tangent line at 0, 0 and at minus 1. So this is kind of a hill, this is a valley. So it has a hill and a valley. And that's a maximum in that little small interval, and a small interval around 1, it is a minimum. Now we will use this, as I said, the critical numbers to find the test interval. So this is the point, that means function from minus infinity to 0. You can see from the graph it is increasing. Then the interval from 0 to 1, the graph is decreasing. And then from the interval from 1 to infinity, the graph is increasing. We already see that in this graph. Now we're going to prove it, with that guidelines using analytic approach. Okay, remember what were our two critical numbers? 0 and 1. So what I normally do is I create a little number line and write the critical numbers. And then when I'm writing my test intervals, so what I do is to remind myself that this is a critical number. I will draw a rectangle so that I do not make a mistake. That's one way also of doing it, and write critical numbers on the top. I like to have some visual representation, so this is my visual representation. Or we can draw it over here too. I can draw this graph for you guys here. So it helps me to get the right intervals. And when I draw it, I'm very, make sure I say, okay, this is a critical number. And on 1, I also create a little rectangle and say, this is my critical number. Okay. So notice, so I have my little picture. At the same time, I'm creating a table. So now, when I have my critical numbers 0 and 1, so I will say, okay, the part from negative infinity to 0 is one test interval. Second grows from 0 to 1. So we can draw a little this. So first interval is 0 to 1. So this is the minus infinity to 0. The second one is from 0 to 1. So that's the second test interval. And the next one is 1 to infinity. Okay. Now, we pick up one value at each of these test intervals. So pick up an easy one, minus 1 over here. So I'll use it with a dot, minus 1 says 0.5 or half, and in the other test interval say 2. So these are my test interval points. To make a distinction, so I say my crosses are test interval points. I like to see what I'm doing. That I'm a more visual person, so I like to see things. Okay, now what are we going to do? We're going to look at the sign of the derivative of the function at each of these test values. So f prime of minus 1 is 6 greater than 0. That means function is increasing. F prime of half is a negative. That means function is decreasing. And f prime of value at 2 is 6. Definitely function is increasing. So to write the increasing and decreasing, so this is what we do. We say the increasing part, the open intervals of increasing are minus infinity to 0 and 1 to infinity. That's my increasing. What about decreasing? So what is the decreasing open interval? It's from 0 to 1. So here we have the open intervals from -infinity to 0 and 1 to infinity. Clearly, this table and this little visual, representation gives us all the answers. So you can do either way, whichever you guys are comfortable with, you can do it. Many times I use these symbols, so you're more than welcome to use these symbols. For increasing, I use an up arrow. And for decreasing, I use a downward arrow. Trying to save time, not to write. Yeah, that's what I can. So this one I can say, hey, this is like I'm saying, this is a downward symbol. It's a decreasing. And increasing is the one which is going up. Either way, whichever you want to write it down, you want to use that arrow, I'm fine with it. Okay, guys. So the next problem. Here, find all the open intervals on which this function x plus 9 over x is increasing or decreasing. Now remember, this function is going to have a bumpy ride at x is 0. Remember, this function is not defined over there. So you have to be very careful. You have to keep this in mind when we are creating a test intervals. Let me show you a graph of this function. You see this graph? Clearly, the 0 is like a vertical asymptote. And notice the graph. So this is the graph, and then you see intervals, you see this graph going up and then it goes to down about some point over here. Similarly, the graph grows, decreases after 0 to some point over here between 0 and 5, and then it starts to increase. So so we need to find which is this point and the point over here where there's a change in the direction of the graph. And remember, nothing is happening at 0. So we have to make sure that point also is taken into consideration when we are doing our analytical approach of getting solutions. Okay, so let's go at this point. So we know that at x equal to 0, this first of all is not in the domain, so it's like a vertical asymptote, and I also showed you the graph. So the graph goes like this. So we are trying to find this point and this point where there is a change. Okay, so what do we do? Oh, the 0 should be here. Okay, so we take the derivative of this function, which is 1 minus 9 over x squared, or x squared minus 9 over x squared equals 0, or x is plus minus 3. Okay, so this basically means is x squared minus 9 equals 0, or x squared equals 9, and then x equals plus minus 3. Now, remember, because this point 0 is like a barrier, so we have to put that in our little table when we create those intervals. Okay, so as I said, when I do these problems, I always create my little picture. So I'm going to make the little graph, and then we can do this too. So here's my graph, guys. We know the critical numbers are x equals plus minus 3, and 0 is a discontinuous point. So what I'm going to do is I'm going to write minus 3 and positive 3. Now remember, these are critical numbers, so I'm using some little geometrical objects to remind me that this is a critical number. I draw a rectangle and a critical number. Now there's a 0 is something which is a discontinuous point, so I can say create a little triangle for discontinuity. Okay, so I'm saying, okay, this triangle represents discontinuity. It is just for my own, little hints that say, oh, this is discontinuity, this is this. So now that tells me what are my 4 intervals. Minus infinity to minus 3, so that's 1. Second is from -3 to 0, then 0 to 3, and 3 to infinity. So I will have 4 test intervals. Now I'm going to pick up a point in each of these test intervals. And remember what we were doing. We're using a little cross. -4, that's a test value or test point or test value. Between -3, I'm going to put -1. Between 0 and 3, a 1. And after 3, I'm going to pick up a point 4. So what we're going to do is, we're going to evaluate the derivative. Very important, it is a derivative at -4. The derivative evaluated at -1, the derivative evaluated at 1, and the derivative of this function evaluated at 4. So when you evaluate the derivative at -4, it's a positive number. That means the function is increasing. When you evaluate the derivative at -1, it is negative. The function is decreasing. When you evaluate the function at 1 again, remember it's because of this barrier by 0, because it's a discontinuous point. It's a vertical asymptote if you remember from the graph. This one again is decreasing. So I'm using my little symbols to remind me decreasing, increasing. And f prime of 4, the function is positive. It is increasing. Now I have to write down the open intervals. I'm going to write, this is my increasing, remember. The intervals are -infinity to -3, and then 3 to infinity. Now where is the decreasing? Now you have to be careful. You cannot include 0 because 0 is not in the domain of the function. So you have to write like this, -3 to 0 and 0 to 3. You cannot include 0 because if you write -3 to 3, it means that 0 is in the domain of the function, where it is not in the domain of the function. So please keep that in mind. Okay, so we had an example where we had critical numbers and we also had some discontinuities. Now let's look at another example, which is a trigonometric function. So it's a sine curve, sin x -1, and we're going to be looking at the interval from 0 to 2 pi. We like to know the open intervals where the function is increasing or decreasing. Now remember what we always do? We look at a graph to have a feel of it. Okay, so let's look at the graph. Here is the graph of the function because we're going from 0 to 2 pi. 2 pi is 6 point some value. So notice the curve goes from, because it's sin x -1. It goes up, then it goes down, then it goes up. So clearly from 0 to somewhere here, that's pi halves, we can see the function is increasing. Then from pi halves, we go down to 3 pi halves, the function is decreasing. And then from 3 pi halves to 5 pi halves, the function is increasing. But 2 pi is somewhere in between. 5 pi halves is more than 2 pi. Okay, so we already see from the graph, function increases, decreases, and increases. So we should be able to also mimic that when we do apply the test, the guidelines to find the test for the increasing and decreasing intervals. Okay, let's do that. Now clearly this function is continuous throughout, differentiable throughout, no problems. We have already seen the graph too. So to find the critical numbers, we're going to do is take the derivative, which is cosine x, put that to 0. Now remember cosine x is 0 at what? Pi halves and 3 pi halves. So what I'm going to do is I'm going to create my little interval. Start from 0, pi half, and 3 pi halves. Now remember these are critical numbers. So I'm keeping my little rectangle boxes and say this is critical number, critical number. Now so the intervals are from 0 to pi half. Now remember this is not including, okay, 0 to pi half, pi half to 3 pi halves and 3 pi halves to 2 pi. Our graph only is from 0 to 2 pi. We have to pick up test values. Now remember what we have been using is a little cross, So pi fourths, pi, and this is 7 pi fourths. Okay, then what we do? We test the sign of the derivative of the function at pi fourths, pi, and 7 pi fourths. So when you look at the derivative of the function at pi fourths, that means it is cosine pi fourths, which is 1 over square root 2. Remember, it is cosine pi fourths. Guys, it is f prime. It's positive, function increasing. And we knew that also from the graph. Remember, the graph looks like this. From 0 to 2 pi. That's how the graph goes. So remember, this was pi half. And this was 3 pi halves. And this one was 2 pi. And this is 0. This is minus 1. Okay, so let's look at when we evaluate the derivative of the function at pi. That means cosine pi, which is minus 1, negative. Now evaluate the derivative of the function at 7 pi fourths, which is cosine 7 pi fourths, 1 over square root 2, positive, increasing in the interval from 3 pi halves to 2 pi and decreasing in the interval from pi halves to 3 pi halves. So let's write it down. Increasing the intervals is from 0 to pi halves and 3 pi halves to 2 pi. Now decreasing, it is from pi halves to 3 pi halves. Now you can see from the graph also. Okay, so now we have learned about how to find the open intervals where the function is increasing and decreasing, and we are using derivatives to find those. The signs of the derivative tells where the function is increasing or decreasing. So now what we're going to do, guys, we are going to look at practice problems. Okay. So I would like you guys to practice these problems. Thank you.